Okay, so the very first thing I'm going to do is I'm going to sketch myself a diagram of the situation. And in this case, we have this mass hanging off the edge of the roller, which they're saying we can treat as a homogeneous cylinder. And because of that statement, I know that the moment of inertia for that cylinder relative to its center of mass is given by the equation of 1/2 mr squared. And so I've jotted that down. And then I've just reminded ourselves that if the string doesn't slip on the edge of the cylinder, then the linear acceleration, in this case of the mass going down, is going to equal the angular acceleration of the cylinder times the radius r. So let's see how we're going to apply those. First of all, I'm going to sketch a free body diagram of both the hanging mass, which the two forces acting on it are mg down and tension up. And of course, I'll designate a positive direction of down in this case, because I always tell my students, make the positive direction the direction of the acceleration, if at all possible. And so then just writing an F net statement, or net force statement, I get mg minus t. The F net equals the m. I'm going to put a subscript 2 there to remind me that it's the 2 kilogram mass that I'm finding the mass of there, equals the 2 kilogram mass's weight minus t. And then, of course, rearranging that for tension, I get the m2g minus m2a. So the reason I'm doing this is because as I turn my attention to the cylinder, notice that the tension is also acting on the cylinder at a point perpendicular to the cylinder. And so that means I can now write a net torque statement for the cylinder. Now I could write an F net statement for the cylinder, but because we're left to assume that it's somehow fixed to a point where it doesn't fall, that's just going to be a net force of 0. And so I can turn my attention to the rotation with a net torque statement. And of course, whatever force is holding it up is acting at the center of mass. And so that's one of the many reasons I'm going to choose the center of mass as the reference point. The other one being that I know the moment of inertia relative to the center of mass. And so when I look at the torques acting on the cylinder, there's just the one caused by tension. It's a distance r away from the center of mass, and its magnitude is tension, whatever t is. And then, of course, times sine of 90, since it's a cross product, and the angle between r and t is 90 degrees. So sine of 90 becomes 1. And I'm just left with this very brief net torque statement. Well, by Newton's second law for rotation, I know that net torque equals I alpha. And now I can substitute the moment of inertia, 1/2 mr squared, equals RT. And then I'm going to substitute A divided by R for alpha. So 1/2 of m r squared A over R equals RT. Canceling out r's, since those are all the same r, the radius of the cylinder, I get this statement. And now you can take it home from here, right? I've got 1/2 ma equals t. And from my other equation, I know m2g minus m2a is also equal to t. I should go ahead and point out, though, this is mass 9, because it's the mass of the cylinder and not the mass of the hanging weight. So I can keep those two m's straight. And now I just substitute this statement for t, and combine those two equations and solve for A. All right, good luck.